Math 2414, Calculus 2, Calculus 1 review, the fundamental theorem of calculus, part 2. This is just some examples. Geez, how many videos have I done so far? 5, 6, 7, 8, 9. I think it's number 10, and I've got some more to go. Don't worry, most sections we cover will not be, oh gosh, 10, 11, 12, 13, 14. I'm anticipating this review to hit about 15 videos, but most sections will contain probably 6, 7, maybe 8 videos total. But reviewing Calculus 1, you should expect a lot of videos. All right, so we're going to apply the fundamental theorem of calculus on these 3 examples. We're going to find a couple of derivatives and evaluate a definite integral. The definite integral will actually be pretty easy, but I want to make a point with it. Well, let's get back to find the derivative of these guys. Find the derivative of g of x equals the integral from 1 to x of the square root of 1 plus t squared dt. Now, if you didn't have the fundamental theorem of calculus, you would have to first evaluate this by finding an antiderivative, which although it's not impossible, it's not possible using techniques learned in Calculus 1. Then you would have to evaluate it at these guys and then take the derivative. But fundamental theorem of calculus part 1 says we don't have to, part A says we don't have to do all that. If you're defined as the definite integral from 1 to x of a function, then the derivative is just that function on the inside evaluated at x. So 1 plus x squared, and it's over. And it's actually pretty easy to verify that. Although the problem is over, the reason it is if we did have an antiderivative, then, well, I'm not going to go down that path. We have this part, so we don't have to find the antiderivative. But that's all the fundamental theorem of calculus part A says. If your function is defined as the integral from 1 to x of another function, then the derivative of your first function is just the inside function evaluated at x. That's all it says. And you might think part B is the same song and dance, and for the most part it is, except there's one important difference. Do you notice the biggest difference between part A and part B? And I'll give you a hint, it is not the integrand. I know it's different, but that's not the important difference. The important difference is the upper limit of integration is not just x, it is x to the 4th power. Now, the fundamental theorem of calculus says what to do if my function is defined from some constant to x, not some constant to x to the 4th. So how can we accommodate this? And the answer is the chain rule. Now, wait a second, why is this a chain rule thing? Well, here's why. I'm going to develop how to do this, and then I'll just tell you the quick way at the end. In order to use the fundamental theorem of calculus, this has to be just a single letter. So we're going to define a new function. We'll call it h. But we're going to define h of u to be the integral from 1 to u of secant of t dt. So I kept the integrand the same, I kept the lower limit the same, but I'm just redefining a new function that has a single variable in the upper limit because that's what the fundamental theorem of calculus can accommodate. But how do we write g? Well, then g of x is equal to h of x to the 4th. Let that sink in. If I put x to the 4th in for the u, then I get this function. So why is this important? Because now I can use the chain rule. And remember how the chain rule works. Derivative of the outside, leave the inside alone, times the derivative of the inside. But how do we do the derivative of the outside? In other words, how do we do the derivative of this? Well, the derivative of this is exactly what the fundamental theorem of calculus gives us. The derivative of this would be secant of u. But what do I have instead of u? X to the 4th. And I already told you in a previous video how I feel about putting things after trig functions. So I would write this as 4x cubed secant x to the 4th. So it does use the fundamental theorem of calculus, but we had to kind of trick it into using it by defining a similar but different function that had a single variable up there, then rewriting the original function as a composition, new function composed with x to the 4th, and then executing the chain rule, derivative of the outside, leave the inside alone, and then times the derivative of the inside. And then when we did the derivative of the outside, that's where the fundamental theorem of calculus came into play. So what's the quick way? Quick way is real simple. If your function is defined as the integral of something from one to another function, fundamental theorem of calculus says just stick this upper limit in there, and then the chain rule says times the derivative of its inside. All right, so that one threw you for a loop. Just stick this into there and then chain rule it. That's all. All right, for the last part, we'll use part B of the fundamental theorem of calculus, evaluate this definite integral. This might be something that looks pretty familiar. I'm going to make it from 1 to, if you've already tried it, I don't want to change it. We'll keep it from 1 to 2. If we do the fundamental theorem of calculus, we'll get an answer, but I want to remind you what this means. This means if we were to graph f of x equals 2x plus 1, which is a pretty easy graph to draw. It's in slope-intercept form. The y-intercept is 1. The slope is 2, which means we would run 1 and rise 2. And then we could do that again. So what would these points be? That would be 0, 1, 1, 3, 2, 5. We could also stick in 0, 1, and 2 into the function. But we're being asked, what is the area under here? Under this line from 1 to 2. As a geometry problem, we can find the area of this trapezoid. The area of the trapezoid is 1/2 times the height times the average of its bases. Or if you just wanted to look at it this way, it's a rectangle minus that triangle. The area of the rectangle is the length, which is 1, times the height, which is 5. So it's 1 times 5 minus the area of the triangle. But the area of the triangle is 1/2 times its base times its height. Its base is 1. How tall is its height? Well, this is 3, the total thing is 5, 5 minus 3 is 2, so if you clean all that up, you get 5 minus 1, which is 4. So that's what this is asking, is what's that area, and if you didn't follow all the geometry, don't panic. All I wanted to do is remind you that we're calculating an area, and sometimes you can find it using geometry instead of calculus. But if we were to use the fundamental theorem of calculus, we better get an answer of 4. So all we have to do is find an antiderivative, find something whose derivative is 2x plus 1. Well, without much to do, x squared plus x will get the job done. The derivative of x squared is 2x, the derivative of x is 1. And then we're going to evaluate that from 1 to 2. And you may remember the notation of putting a vertical line with the limits of integration on the bottom and top of it, meaning that we're going to evaluate this at 2, evaluate it at 1, and subtract the results. If we evaluate it at 2, we get 2 squared plus 2. If we evaluate it at 1, we get 1 squared plus 1. 2 squared plus 2 is 4 plus 2, which is 6. 1 squared plus 1 is 1 plus 1, which is 2. 6 minus 2 is 4, thank goodness, because geometrically that's what I thought. So yeah, fundamental theorem of calculus. More often than not, we're going to be using it in this capacity than that one, which means how do we find the antiderivatives? Well, it would be nice if we had some integration rules. Oh wait, we do.